So the next thing is the types of reactions, and mainly there would be 7 different kinds of reactions: precipitation reaction, acid-base neutralization, redox, double replacement, single replacement, combination, decomposition. A detail for these is provided in this YouTube screencast that I developed for you, where I get you started on the difference between the acid-base neutralization reaction and precipitation reaction, both of which are forms of double replacement reaction. And then single replacement, of course, is a kind of redox reaction, but we are going to discuss that in a little bit more detail in the next week's next week's aspect on Blackboard. Of course, we always have the decomposition and combination, which are opposite of each other. So we'll be discussing each one of these, but feel free to access this YouTube video to first get a feel for what is the basic difference between acid-base neutralization and precipitation. How do we go about that? Now, first things first, the one thing that you can look for a double replacement reaction is essentially that you would begin with 2 compounds which will have a positive end and a negative end. For example, I'm showing you a lead nitrate and a potassium iodide, both of which contain a cation and an anion. So you can consider these as 2 like dancing partners, and after the reaction takes place, basically they have switched their ionic partners. So now Pb is dancing with I, giving you PbI2, and potassium is dancing with nitrate. So that is why, since it's a double displacement that both of the salts participated in, we use the word double replacement reaction. In terms of, so just taking you back one more time, if you had to predict which one of the 2 products is going to be the solid and which one will be the AQ, please realize that AQ are the letters that we use for when it's completely soluble in water. So there are, of course, solubility rules that are associated with it, which are given through a screencast to you under the content section, as well as on this slide. You can simply click on that and access the solubility rules. But in general, always remember that all nitrates, perchlorates, chlorates, acetates, bicarbonates, those are soluble, and that means that this lead 2 nitrate is going to be something soluble, as would be the potassium nitrate. Also, group 1 cations, if that is present, so some kind of sodium potassium group 1 cations, those are going to be completely soluble as well, and that leaves lead iodide as the solid, as the insoluble material here. So you should know how to classify that, and I'm going to jump through slide 22, 23, and 24, which is where these rules are stated, and I go over these rules. I provide you the entire explanation in that screencast. Please view that, because I take the time to explain what's why and how. But this is the kind of question that you can expect in a test where you're expected to predict the solubility of a particular compound. So for instance, in this case, it says cadmium carbonate. Carbonates, until and unless it's an alkali metal carbonate, till the time you can simply consider that most of those will be insoluble. So this is an insoluble. Magnesium oxide, just to give you a flavor, that is a component of Pepto-Bismol, for example, and the likes of those. So those are insoluble as well. Sodium sulfide, the moment you see a group 1 cation, irrespective of what the anion is, it always will be soluble. Lead sulfate, this is the case of the exception. All sulfates are soluble other than when it's a lead, silver, or mercury. So this is the case where you have insolubility. So insoluble, BLE. And last one is ammonium phosphate. Ammonium tends to behave the same way as group 1, and hence this will remain soluble as well. Going forward, the next question asks you, write the balanced reaction and predict whether a precipitate will form here. So you're given that you have nickel 2 chloride that's reacting with ammonium sulfide, and we want to predict the product, we want to balance it out, and then we want to predict which one is going to be the precipitate. So realize we have a cation and an anion in both these cases. So this is of the perfect format of a double replacement reaction, specifically precipitation reaction. So all you gotta do is you have to predict the formula for the products. So nickel in the +2 state is reacting with S2 negative. Let's write that somewhere. Ni as 2 plus is reacting with S2 negative. That means the formula for the nickel sulfide, or nickel 2 sulfide rather, is NiS. And you have NH4 twice and Cl2 twice. That means you are going to end up with 2 NH4Cl, ammonium chlorides. So ammonium salts always soluble. That means this is going to remain aqueous, and sulfide, until and unless it's ammonium or group 1, will always remain insoluble. So your solid component, something which will precipitate out in this reaction, will be the nickel 2 sulfide. Based on the principle, let's see if we can predict what's going on in the second one. We have lead 2 nitrate, which is reacting with sodium chromate. So my possibilities are that the sodium is going to react with NaNO3, with NO3, the nitrate component, to give you NaNO3, and you're going to end up with 2 moles of that. You're going to get 2 moles of that. Let's try to write that again. That's very strange. Okay, 2 moles of NaNO3, and in addition to that, you're going to get PB, CrO4. And the reason why I write that as a formula is because lead is in the Pb2 plus state, and CrO4, which is chromate, is in the 2 negative state. And when you combine the two together, your formula will start looking like PbCrO4. Again, realize all sodium salts are going to remain soluble, so the sodium nitrate is going to remain aqueous, whereas the lead chromate is going to be solid. The last one, if you think about it, we have given you silver chlorate, silver 1 chlorate to be precise, reacting with CaBr2, and so it's going to give you CaClO4 twice plus AgBr. In order to balance, you will need 2 moles of AgBr, and you will need 2 moles of AgClO4 as well. So let's write that too somewhere in front of that to completely balance it out. And now we have to predict which one of the two is going to be the precipitate. So realize all perchlorates are always soluble, so this is going to remain aqueous, whereas silver bromide, that is going to precipitate out as the solid in this case. All right, the next couple slides, which is slide 27, 28, they are based on the conversion of a molecular equation into an ionic equation. The word molecular equation is specifically for balanced reaction, and I do have a screencast for this part as well. But here I'm showing you FeBr3 with lead nitrate, giving you iron 3 nitrate and lead 2 bromide. Now realize a couple things. The first thing that you need to worry about is to make sure that, to basically verify that you have balanced out the reaction. Once you have your balanced reaction, the next step is basically to convert everything that has letters AQ right by it. You should break that, you should split that into the ions, and so it will give you, in this case, 2 Fe3 plus. 2 times 3 will give you 6 bromides, and then we have 3 lead. So because you have two nitrates with it, the charge will be 2 plus. That means you'll have 3 Pb2 plus 3 times 2, that will be 6 nitrates, will give you 2 Fe3 plus 6 nitrates plus 3 PbR2 will remain as is because it has the subscript S for solid. Now we look for the bystander ions in this complete ionic equation. Bystander ions, also called as spectator ions, are those that are that basically exist on both the sides of the equation. So those are nitrate and iron in this case, and so they will cancel out, and what remains is going to be your net ionic equation. So the last equation, like I said, net ionic equation. Notice in the right hand side you have PbBr2, which was the solid component, and on the left hand side you only have the ions that are responsible for that final product. So so realize that's one way to kind of cross-check for yourself whether the final equation that you got for this precipitation reaction, whether it came out right or not. Like I said, there is a screencast on that, so please make sure you watch it in good time, so so you know exactly how to go about it through a different example, of course. And so here's the video link that you can go to access in your own time and essentially view, what we have for another set of equation. Let's for the time being work on another one. The question here is, write the net ionic equation for the following, and you're given the equation that you have 2 silver nitrate reacting with sodium chromate to give you silver 2 chromate and sodium nitrate. So the first things first, you have to check whether or not it's a balanced equation, and I'm telling you in this case it is. What's the next step? The next step is to break up everything which has the letters AQ into smaller ions, and so you will see, let's just write that down. You are going to see 2Ag plus 2 nitrate. I'm going to just put that in parentheses because it doesn't allow me to show the superscript and the subscript at all times, and a negative sign. Of course we are going to have 2 sodium pluses plus CrO4 with 2 negative charges. That's what we have on the left hand side, and on the right hand side I have Ag2CrO4, which is the solid, and we have 2 sodiums, of course, and with that we have 2 nitrates as well. And notice the nitrate and the nitrate are going to cancel off each other. The sodium and the sodium will cancel off each other. What will remain will be 2Ag plus CrO4 2 negative, and that will come together as Ag2CrO4, and that will be your solid. So the first complete equation is the complete ionic equation, that is your CIE, and the final equation is going to be your NIE. So you should know how to recognize that, which ones to cancel, and the likes of those.